Okay, so we're going to talk about fatty acids. I remind you that fatty acids were the second of four major groups of lipids, and we're going to talk about those. They are also components of the glycerides, which we've looked at in the previous video. So what about fatty acids? All right, first of all, they are acids because they have a carboxyl group. Now, a carboxyl group has, it's very poorly drawn, I'm sorry, a carbon double bonded to an oxygen and then single bonded to a hydroxyl group. And that hydrogen there of the hydroxyl group comes off easily, but when it does come off, it turns to the oxygen and says, "Oxygen, I'm leaving. You can keep my electron," which means that hydrogen leaves without its electron, making it positively charged. So that is what acids do. They give off positively charged hydrogen. All right, so to make them fatty beyond the carboxyl group, we need to have a chain of carbons. Now, to be considered a fatty acid, there need to be a minimum of 3 carbons, but realistically, most of them are going to have 6 to 20. As I mentioned earlier, the 3-carbon fatty acid is called propionic acid. It can also be called propanoic acid. The 4-carbon fatty acid is butyric acid or butanoic acid. Beyond that, they pretty much are restricted to even numbers of carbons. So here I have a 6-carbon fatty acid. And what I'm going to do, I'm going to extend this on out and just arbitrarily decide to make it a 10-carbon fatty acid. Now again, we can simplify this by not writing the letter C every time. If I just do a zigzag line, then at each corner of the zigging and zagging and at the end point, it would be implied that there is a carbon there. We also mentioned how carbons must always have 4 bonds. Okay, so we look at the carboxyl carbon over here. It has 2 bonds to this oxygen, 1 bond to this hydroxyl group, and 1 bond to this carbon, giving it 4. This carbon here only has 2 bonds so far, 1 to the carboxyl carbon and 1 to this carbon over here. So it's missing 2. So what we would expect is for that to have 2 hydrogens. Same thing with this carbon. It needs 2 more. It'll have 2 hydrogens. This one only has 2 bonds, so it needs 2 hydrogens. 1-2 bonds here, so it needs 2 more bonds. 2 hydrogens. I think you're getting the picture. I've started down this path. I'm going to go ahead and finish it out and write in all of these stinking hydrogens. All right. And this one at the end will need a 3rd hydrogen to give it a total of 4 bonds. So I'm about to throw out a buzzword here that will describe this fatty acid. It's a word I'm sure you've heard before. Because the chain has only single bonds in it. Now the double bond to the oxygen doesn't count. That has to be there for there to be a carboxylic acid group. But for the rest of the molecule, the chain consists only of single bonds between the carbons. And that means that each carbon has the maximum number of hydrogens bonded to it. So our buzzword here, if you think about, consider a towel. And when that towel has absorbed the maximum amount of water that it can, that towel is said to be saturated. And so when a fatty acid has only single bonds between the carbons, then it will be saturated with hydrogen. So that's what saturated means in terms of saturated fats. It's actually a fatty acid that can be saturated or not. So this is a saturated fatty acid consisting of a chain of 10 carbons. Okay, so how do we get a fatty acid that is unsaturated? Well, it will also have a carboxyl group, or else it wouldn't be a fatty acid. And then we're going to have another carbon, another carbon, another carbon. Let me plan this out. Let me pause for a second. All right, so I have 1, 2, 3, 4, 5, 6, 7 carbons so far. What I'm going to do, again, this is kind of arbitrary that I'm choosing to put it here, but I'm going to put a double bond here at this carbon. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and there's carbon number 10. Okay, so again, let's go through this and figure out how many hydrogens are needed. This carbon here, it only has 1, 2 bonds. It needs 2 more, so we'll put 2 hydrogens. This carbon up here has 1, 2 bonds. Needs 2 more. We'll put 2 hydrogens. 2 more. 2 hydrogens. 1, 2 hydrogens. This one down here has 2 bonds and therefore needs 2 hydrogens. But now, look at this carbon here. Single bond and a double. That's 1, 2, 3. It only needs 1 more bond. It's going to go up this way. We're going to put a hydrogen on it there. Then look at this carbon. It already has 1, 2, 3. It only needs 1 more. We're going to angle it up this way. Come down to this one, it needs 2. And this one needs not just 2, but 3 because it's on the end. Because of this double bond, this fatty acid is unsaturated. Not only that, but there's only 1 double bond in it. Again, remember the double bond to an oxygen doesn't count for whether or not the fatty acid is saturated. It's only the bonds between the carbons that matter. Since we only have 1 double bond here, it's not just unsaturated, it is monounsaturated. A lot of studies through the years have shown monounsaturated fatty acids to be good for cardiovascular health. You'll find a pretty good degree of monounsaturated fatty acids in olive oil. Okay? Now, there are a couple of ways to, well, a couple of things. We need to be able to tell where the double bond is located, because it could be there or it could have been over here. So the 2 ways to indicate where that double bond is located. One is that we start counting carbons and we start with the carboxyl carbon, with it being carbon number 1. So that means this one's number 2, 3, 4, 5, 6, 7, 8, 9, and 10 down here. So we could say that the double bond exists right after carbon number 7 here. Right? But in another system, in an older system, you had your carboxyl carbon, then the one next door to it was called the alpha carbon. Lowercase Greek letter alpha. Some people say it looks sort of like a Jesus fish. The next carbon over was called the beta carbon. The next one was called the gamma carbon. The next one was called the delta carbon, and so on through the Greek alphabet. Except that the one at the far end was always called the omega carbon. If you've been to Sunday school, you know that Jesus said, "I am the Alpha and the omega the beginning and the end. So the carbon at the far end of the chain was always referred to as the omega carbon, regardless of where it actually fell alphabetically. So now, I hear sometimes people, as they're talking about saying that you need to get your omegas, which is a saying that makes my skin crawl. What they mean, what they should be saying, is that you need to get something like this. And what is it about this? If this is the omega carbon, here's the first bond. Here's the second bond from the end. And this bond, the double bond, is the 1,2/3 bond from the end. And that makes this an omega-3 fatty acid. So we could move it. It doesn't have to be here at the third one from the end. It could be at the 6th from the end or the 9th from the end if we had enough carbons. So to say get your omegas is vague. What do you want me to get? Omega-3s? Omega-6s? Omega-5s? What we mean when we say get your omegas is you need to be sure you get some omega-3 fatty acids. And that's what an omega-3 fatty acid is. The double bond that makes it unsaturated is the third bond from the end. And remember that omega is at the end of the Greek alphabet and the end of the chain, far end away from the carboxyl carbon. All right. So, in addition to omega-3 fatty acids being healthy for us, and remember, omega-3s come from fish oil. In particular, fish that live in cold ocean water. So salmon, cod, mackerel, their oil in the flesh and in particular in the liver is going to be very rich in omega-3 fatty acids. Omega-3s are also found in beef, but what the cattle are fed will impact how much omega-3 versus how much omega-6 is in the fat of the cow. Cattle that are allowed to eat grass, the way nature intended, will produce more omega-3s than cattle who are raised and fed a diet of grain. And they will produce more omega-6. The findings are that omega-3s are healthier for our cardiovascular system than omega-6s. Okay, so we've got a couple of buzzwords here. We've talked about saturated fats, and now hopefully you understand what that means. We've seen unsaturated, which means we're going to have some double bonds. Monounsaturated means there's only one double bond. Where the double bond is located is denoted by where is it in relation to the end, the omega end of the molecule. Here it's the third one that makes it an omega-3. We know that omega-3s come from fish oil. That's why you can get fish oil capsules, cod liver oil, etc. Another buzzword, and this is kind of the new darling buzzword in nutrition, health food circles, is going to be this. We see here that around this double bond, the two hydrogens both ended up in the way I drew it. Both those hydrogens are up here on the top side of this double bond. As opposed to, we could have done something like this. Could have come up, gone over to that double bond, and then gone up this way. Okay, to get to number 9, and then from there on to carbon 10. So notice the difference. Both hydrogens on the same side of this double bond. versus down here, one hydrogen on one side, the top side, as if from this perspective, and the other hydrogen down here on the bottom side. So we have some prefixes that let us know whether or not both hydrogens are on the same side or if they are on opposite sides. So the word that means across is trans. And the word that means on the same side is cis. C-I-S. Now the terms cis and trans have come into everyday language here just in the past few years, really, where we talk about someone being a transgender or cisgender. But here in organic chemistry, cis means that two atoms of the same thing, in this case hydrogen, are on the same side of the double bond. And down here, the two things that are the same, in this case these two hydrogens, are across the double bond from each other. Okay, so you can see now foods with a label that says no trans fat or 0 grams trans fat. This is what they're talking about, is does the chain of carbons just zig and zag along, and then if it's cis, you notice that it stays pretty straight like this. Trans, it's going to have to go off at this angle. I need to talk a little more about that difference here. But the health implications are that cis fatty acids, cis double bond arrangements are more heart healthy. And the trans is not healthy for our hearts. Now, trans fats are almost non-existent in nature. I won't say there are absolutely no trans fats that occur in nature, but there are very few, if any. Nature makes cis double bonds. So where do the trans fats come from? Well, they come from man trying to outsmart himself and manipulate these things chemically. There is a process by which a cis fatty acid can be treated with hydrogen in a process known as hydrogenation or hydrogenation. Two hydrogen atoms can be added to carbons, in this example here, carbons 7 and 8, and break the double bond, leaving just a single bond. Well, if you take out the double, leaving it as a single bond, and add 2 more hydrogens to it, you get the saturated fat that you see up here, the saturated fatty acid. By doing that, we cause unsaturated fatty acids, which tend to remain liquids at room temperature, to become saturated fatty acids, and they have a tendency, due to their shape, we need to talk more about that later, but they have a tendency because of their shape to form solids. So when you think of solid fats, things like lard and butter, they are high in saturated fats. And 50, 60 years ago, approximately, scientists decided, hey, we can take oils that have cis double bonds in them. They weren't thinking about the cis aspect of it, I don't believe, but we can hydrogenate that, add hydrogen, break the double bond, and turn those unsaturated fats into saturated ones. Since they were going to get this from vegetable oil, they would be avoiding the presence of another, which is called cholesterol. Cholesterol is normally present in animal fats. So since your saturated fats came from animal sources like butter and lard, they would also contain some cholesterol. So they thought, well, hey, we can take vegetable oil that has double bonds in it, synthetically saturate those double bonds, and there won't be any cholesterol. And they thought they were helping us out health-wise. Turns out, when you don't completely hydrogenate, sometimes those cis double bonds get reformed as trans double bonds. And it has turned out that the trans fatty acids actually trick our liver into making more cholesterol. So we end up with more cholesterol problems from trans fats than we got away from by just not using the saturated fats in the first place. Okay, so saturated, unsaturated, monounsaturated, omega-3, cis versus trans. Hope that clears a lot of that up for you.